Hey, good morning. We're going to take a look at lesson 410, transforming linear functions, and our objective is to describe how changing the slope and the y-intercept affect the graph of a linear function. We've been talking about a family of functions that's a set of functions whose graphs have basic characteristics in common, and the functions we've been looking at come in this form: y equals mx, or f of x is equal to just x, and we can see that that is our basic function in the linear family. The parent function is the one we just talked about. It's the most basic function. For linear functions, we see the parent function f of x equals x, or in other words, y equals x. The graphs of all other linear functions are transformations. So we've been dealing with a lot of transformations. We're going to leave it in slope-intercept form, such as we've looked at functions 2x plus 3, and we understand that 2 to be our m, and that 3 to be our y-intercept, or excuse me, b. There we go. And those tell us important things. So our y-intercept of 3 and our slope of 2, and we can see we have a fairly steep line. So that's part of the family of the linear functions. The graphs of all linear functions are transformations. It's a change in the position or the size of a figure. Since we're talking about lines, we're going to talk about the position, how steep, how less steep they are, etc. There are three types of transformations that we're going to talk about today. They are translations, rotations are just what they sound like, and a reflection. And we're going to talk about reflections across the y-axis, mainly in our journey through lesson 410. The four functions and their graphs below, I see y equals x plus 3. We see a slope of 1 in that equation, and a y-intercept of 3. We see in f of x equals x, that is our parent function, y equals x plus nothing. So that one's in direct variation. We remember that from lesson 4.8 or 4.9, and it's our parent function, and everything else is translated about that one. What we can see is all of these functions, x minus 2 and x minus 4, they're all parallel. We see that coefficient to the x variable is 1 in every single case. And then something happened. We added 3, we added nothing, we subtracted 2, or we subtracted 4. All of the lines are parallel, the slopes are all the same, but the y-intercepts have changed. Here are the graphs of three different lines: x plus 3, x minus 2, and x minus 4. Again, the one thing I want you to notice is the slope of each one of those is 1. The slope is 1, 1x plus 3, 1x minus 2. They are vertical translations of the graph of the parent function y equals x. When we talk about translations, we're talking about moving every point of the line the same distance, in the same direction. You can think of it as a slide. So notice our blue line, our parent function. The top one, x plus 3, we can see slid a distance of 1, 2, 3 units. That would make sense, wouldn't it? From the parent function y equals x, we can see the blue line slid 1, 2 units down to get parent function minus 2. And we can see that x minus 4, from the parent function, we slid 1, 2, 3, 4. So that value at the end of our parent function, y equals x, plus or minus that b value, tells us the direction and the distance of the translation or the slide. Vertical translation of a linear function is when the y-intercept b is changed From the slope-intercept form, y equals mx plus b, the graph is translated vertically if b increases, as we saw in the function y equals x plus 3, that's an increase of plus 3, the graph's translated up. In the case where b is decreasing, minus 4, the graph is decreasing or sliding down. So plus positive b increases, slides up, negative b slides down. The graph f of x equals x plus 4 and g of x equals x minus 2. Then describe the transformation from the graph of f of x to g of x. Graph these two and describe the transformation from the graph f to g. So you go ahead and do that, stop the recording, graph those, and then be able to tell me what happened from f to g. Well, we're going to take a look. You should have your solution now. From f of x, the blue line, we have x plus 4. We have the parent function plus 1, 2, 3, 4 units up. That's where we got our plus 4. What happened from f of x to g of x? Well, we're not saying from the parent function now. We're saying from the original blue line, what happened? And we see that we slid 1, 2, 3, 4, 5, 6 units vertically down. The graph x minus 2 is the result of translating x plus 4 6 units down. And we can see that's a difference of those y-intercept values easily, quickly. Now we're going to talk about something termed as a rotation. The graphs of g of x equals 3x, h of x equals 5x, k of x equals 1/2 x are rotations of the graph of our parent function, again, y equals x. A rotation is a transformation about a point. So now we're going to maintain a point, and we're going to rotate the graph clockwise or counterclockwise, or turn it, if you will, and the y-intercepts are going to maintain their location, but the slopes are different. So the definition of a rotation, when the slope m is changed in the function y equals mx plus b, it causes a rotation of the graph about the point 0b. We recognize that as our y-intercept, which changes the line's steepness. Now recall back to the previous slides, what was changing was our b value. Our y-intercept changed in our translations or our slides, but the y-intercept or the slope is changing in our rotations. So I want you to think about the graph f of x, 3x minus 1, and g of x, 1/2 x minus 1. And the thing that you should notice right off the bat is that y-intercept on both of those functions is -1. I want you to be able to describe the transformation from f of x to g of x. So they've graphed, and we can see that, of course, the first line with a slope of 3 is our much steeper line. That's rise 3, run 1. And our graph of 1/2 x minus 1, rise 1, run 2, much less steep than the first one. We know that they have those y-intercepts in common, so that's going to be our point of rotation. So if we start with f of x, this is our first one, starting with f of x, what's happening to translate or to rotate to g of x? It says the graph of g of x is the result of rotating the graph f of x about the point, remember 0b, or our y-intercept, 0, -1. The graph g of x is less steep than the graph f of x. So that's what we want to be able to talk about when we talk about rotations. Here you can see our new term. We said we were going to talk about translations, rotations, and finally reflection. The diagram shows the reflection of the graph f of x equals 2x across the y-axis, producing the graph g of x equals negative 2x. And you guys right off the bat have noticed that that slope is just the opposite value. A reflection is a transformation across a line that produces a mirror image. In this instance, our mirror is the y-axis. You can think of a reflection as a flip over a line. For now, we're going to use the y and the x-axis. Later on, we'll use different lines as we get used to this concept. Formal definition of reflection of the linear function: when the slope m is multiplied by negative 1, when the slope is multiplied by negative 1 in f of x equals mx plus b, the graph is reflected over or across the y-axis. So let's look at this situation. We have the graph f of x equaling 2x plus 2. We're going to reflect the graph of f of x across the y-axis. Write the new function g of x to describe the new graph. Well, previously it said we're going to take the form y equals mx plus b. We're going to take that m value and multiply it by negative 1. So we can see in our f of x function we have the slope m equals 2. We take that, multiply it by negative 1. We get our new slope of negative 2 and plug that in. G of x is negative 2x, and we're going to maintain that y-intercept of positive 2. F of x equals 2x plus 2 reflects over the y-axis and results in g of x equals negative 2x plus 2. Let's graph f and g of x and describe the transformation from f to g. Well, we've got f of x is our parent function right down here in blue, f of x. And what's happening when we end up with 2x plus 3, or our red line? Ding-a-ding-a-ding. First thing we're going to do is multiply f of x by 2 to get our new slope. H of x equals 2x. Multiplying f of x by 2 to get h of x, 2x, this rotates the graph about the point 0, 0. They shared that in common. And it makes it parallel to g of x. Then what we're going to do is subtract